Rahim. Assalamu alaikum to all of you. Welcome to the second lecture of Mechanics of Solids. In the previous lecture, we tried to understand why are we studying this subject. Now we are moving towards the answers of what will we study in this and how to approach this realm of knowledge. In this lecture, we will discuss the subject's basic principles and terminologies. These simple yet critical concepts will provide the foundation for understanding upcoming advanced topics. Stay tuned and pay attention so that you get a good grasp of these fundamental ideas. The recommended books for this subject are Mechanics of Materials by R.C. Hibbeler and Strength of Materials by Andrew Peitel and Ferdinand L. Singer. Other sources are also available, but I have found these two to be very student friendly along with providing a comprehensive outlook on the subject. We will formally start our lecture. In this lecture, we first need to understand what is the difference between rigid and deformable bodies. Basically, there are three fundamental areas of engineering mechanics. These are statics, dynamics, and the strength of materials. Statics and dynamics are devoted primarily to the study of the external effects of forces on rigid bodies. That is, the bodies for which the deformations or the change in shape can be neglected. In contrast, the strength of materials deals with the relations between externally applied loads and their internal effects on bodies. Moreover, these bodies are no longer considered rigid. We need to consider the deformations that are occurring in these bodies. This means the deformable bodies. For example, if you are designing a structure, you don't want any beam to deform excessively or to fail by breaking. The difference between rigid body and the deformable body can be understood by using this simple bar example. You can see here that this bar is supported at this point using this pin support and it has been loaded with this weight W. We need to determine what will be the force P that is used to support this bar. Support this weight W. It is a simple problem in statics to determine the force required to support this load. A moment summation about the pin support determines P. This static solution assumes the bar to be both rigid and strong enough to support the load. However, in strength of materials, the solution must extend further. We must investigate the bar itself to ensure that it will neither break nor be so flexible that it bends without supporting the load. Expecting that you would have already studied how to analyze rigid bodies in your engineering mechanics course. In this course, we have to learn analysis of deformable bodies. Thus, in the beginning, we will review some of the basics of statics to understand how can we analyze the deformable bodies. The first thing that we need to understand is the external loads. A body is subjected to only two types of external loads, namely surface loads or the body forces. Surface forces are caused by the direct contact of one body with the surface of another. In all cases, these forces are distributed over the area of contact between the bodies. If this area is small, in comparison with the total surface area of the body, then the surface force can be idealized as a single concentrated force. However, we will discuss the types of surface forces in the upcoming slide. In this slide, we only need to understand what is a surface force and what are the body forces. The body force is developed when one body exerts a force on another body without direct physical contact between the bodies. Let's take an example. This is a block on a ramp. There are three types of forces occurring on this block. One is the normal force of the ramp, the other is the frictional force between the block and the ramp, and the third one is the weight of the block. These first two forces, the normal and the frictional forces, depend on the surface area between the block and the ramp, and thus these are the surface forces. The weight of the block is the body force. As I've already mentioned that we are having two types of surface forces. These are the concentrated force and the linearly distributed force. In this example, we can see that this is the concentrated force. If the area of contact between the two surfaces is very small as compared to the applied force, then we call that this is the concentrated force. One such example is the force exerted by the ground on the wheel. That is a concentrated force. Second type of surface force is the linearly distributed load. If the surface loading is applied along a narrow strip of the area, then the loading can be idealized as a linearly distributed load. Here, the loading is measured as having an intensity of force per unit length along the strip and is represented graphically by series of arrows along the line S. The resultant force Fr of Ws is equivalent to the area under the distributed loading curve, and this resultant acts through the centroid or the geometrical center of this area. One example of linearly distributed load is the load acting on a beam, and this idealization is often applied in the analysis of beam. The third type of force, or the second type of external load, as we have discussed, are the body forces, and then some examples of the body forces are the Earth's gravitational force, the Earth's electromagnetic force, and we also need to remember this thing that Earth's gravitational force basically acts through the center of gravity of the body, or the weight acts through the center of gravity of the body. I'm highlighting these points because we have to utilize these points in upcoming lectures. The next thing we need to understand are the support reactions. The surface forces that develop at the supports or points of contact between two bodies are called reactions. It is necessary to understand that if the support prevents translation in a given direction, then a force must be developed on the member in that direction. Likewise, if rotation is prevented, a coupled moment must be exerted on the member. For example, if a roller support is preventing translation in this vertical direction, then it must exert a vertical force on the beam at this point. Similarly, if this fixed support is resisting a vertical force, a horizontal translation, a vertical translation, and a rotation, thus it must exert these three types of forces: the horizontal force, vertical force, and the moment. Same goes for this internal pin. You know this thing that a pin cannot support a moment. So this pin can only prevent a horizontal motion, a vertical motion, and thus these two types of forces will be developed at this pin location. Equilibrium requires that sum of all the forces acting on the body must be equal to 0. This means that the vector sum of all the forces must be equal to 0. Here we can see here that this is the bold-faced letter, which means that the vector sum of forces and the moments acting on the body must be equal to 0. If we establish a x, y, z coordinate system, then we can decompose these equations in this scalar form, and sum of forces along the x, y, z axis must be 0, and same goes for the sum of moments along the x, y, and z axis. Now, it is vital to remember this thing that we must understand that how can we establish the direction of movement. Moment direction can be established by using the right hand rule. If you curl your fingers in the direction of rotation of movement, your thumb will point in the direction of the moment vector. Like if you curl your fingers here along, if you curl fingers of your right hand along this vector, along this direction of rotation, your thumb is pointing in this x direction. This means that this is the mx moment. Similarly, if you curl your fingers in this direction and your thumb is pointing in this vertical direction, that it means that it is my moment. It is necessary to understand this basic principle because it will establish or it will help us to distinguish between the different types of bending moments and the twisting moment. Here we can also see this thing that we are having the positive direction, force and moment, and the negative direction will be on the opposite side of the origin. It is quite often that the loading on a body can be represented as a system of coplanar forces. Coplanar forces means that the forces are lying on a single plane. As we can see in this figure that these two forces are lying on the xy plane, which is a single plane. There is no force in the yz or the xz plane. But at the same time, the moment acting in the presence of these two forces will be the mz moment, or the moment acting along the z-axis. We need to understand this thing that this is the most common phenomena in engineering practice, and we will be dealing mostly with this type of force system in which the forces will be along the x and y axis and the moment will be acting along the third or the z axis. In order to successfully apply the equations of equilibrium, we first need to specify all the known and unknown forces that act on the body. And the best way to account for all these forces is to draw a free body diagram of the body. For example, if we take a look at this block that is being pushed by this man, we can see here that there are four different types of external forces acting on this body. One is the friction between the block and the floor. The other is the force of this push, the vertical force of the floor, and the weight of the block. In this way, if we divide all the forces acting on a body and represent this using a free body diagram, we can easily analyze a body for the internal effects and to ensure that the conditions of equilibrium are satisfied under all conditions. Now we will study how can we determine the internal resultant loadings. Consider this three-dimensional body of arbitrary shape. Statics require that the summation of the external forces, it is F1, F2, F3 and F4 should be 0. However, in strength of materials, we will go deeper. We need to determine that if a section is cut across the body, the internal forces acting on the exposed surfaces are enough to ensure the equilibrium of both the segments. Although exact distribution of forces is not known, we may not know how the internal forces are distributed, but we can use equations of equilibrium to relate the external forces on the bottom of the body to the resultant force and moment at a point O. This point O is usually taken as the centroid of the sectional area. If a member is long and slender like a beam or a rod, the section to be considered is generally taken perpendicular to the longitudinal axis of the member. This section is often referred to as the cross section. Resultant force and moment can often be resolved into the components that are either perpendicular or tangential to the section. Based on this distribution, then we are having four types of internal loadings. These are the normal or axial force, shear force, torsional moment, or the bending moment. The first type of internal loading is the normal force. Normal force develops when an external force tries to pull or push the body. On the other hand, shear force often develops when the external loads tend to cause the two segments of the body to slide over one another. You must have noticed shear force in beams when a vertical loading acts on a beam. Secondly, shear force is also observed in the bolts that are used to join two pieces of two different materials. The force that is ripping the bolts apart is often a shear force. Moment, it is necessary to understand the direction of moment vector to determine whether it is a bending moment or a torsional moment. A bending moment acts when the direction of moment vector is perpendicular to the longitudinal axis. Like in this diagram, it can be seen that the bending moment is mz because this z is perpendicular to the longitudinal axis. On the other hand, a torsional moment acts when the moment vector is parallel to the longitudinal axis. Like in this mx is the torsional moment because it is acting parallel to the longitudinal axis. Bending moment acts, for example, when a vertical load acts on the centroid of the beam. This type of force causes a bending moment. On the other hand, if a force acts in a way that it is not on the centroid of the cross section, it is away from the centroid of the cross section, then in addition to generating bending moment, it will also generate a torsional moment. This type of moment will be generated, which will cause twisting of the beam or the structure. Subjected to a coplanar system of forces. Coplanar, as I already mentioned, are the forces that act in only one plane. Then only normal force, bending moment, and shear force will exist in the section. If we use the xyz coordinates, then n can be obtained by applying the force in this x direction, or the summation of forces in the x direction. V can be obtained by applying a summation in the y direction, summation of forces in the y direction, I must say, and the bending moment can be obtained by applying a summation of moment at this point O. You are given the task of determining internal forces on a section of a body, then you need to follow these three steps. In the first step, determine the support reactions. First of all, decide which segment of the body is to be considered. If the segment has a support or connection to another body, then before the body is sectioned, it will be necessary to determine the reactions acting on the chosen segment. To do this, we need to draw the free body diagram of the entire body and then apply the necessary equations of equilibrium to obtain these reactions. How can we apply these principles? We can learn it by using an example, and we have done some examples in the upcoming slides. This problem, it has been stated that we need to determine the internal resultant loadings on the cross section at C of this cantilever beam. We can see here that this is a fixed support here at this point A. This means that vertical, horizontal translation as well as rotation at this point will be restrained. The loading applied is a uniformly varying load. First step is the determination of support reactions. However, we can see here that we need to section at this point C. If this segment CB is considered, we do not need the support reactions at the point A. Thus, it means that prudent choice of the segment can ensure minimum calculations. So we can skip the determination of support reactions and we can move towards the next step, that is the free body diagram. If we draw the free body diagram of this section CB, we will know that the first step is the determination of the load intensity at this point C. Because this 270 Newton per meter is the load intensity at point A. How can we determine the load intensity at point C? By using the similarity of triangles. So 270 over 9 will be equal to LC. LC is the load at this point C over this distance, that is 6. So LC comes out as 180 Newton per meter. This thing that we need to determine the resultant force and the moment at the centroid of the cross section, and the centroid of this cross section CB will be at point 2. At the distance of 2 meter from C, because the loading is triangular. If this loading would have been rectangular, this central point would be at 3 meter from point C. Thus, the resultant force acting at 2 meter from the point C will be 540 Newton. How have we determined this? This is simply the load distribution or the area under this particular loading diagram. 1 by 2 into LC, the load intensity at point C, into 6, this length, and this comes out as 540 Newton. Now the final step, that is the determination of forces acting on point C. Summation of forces along the x direction shows that there is no force in the x direction at point C. Summation of forces along the y direction shows that if downward forces acting at this point at a distance of 2 meters from the point C, then it means that an upward force will act at point C to maintain equilibrium. Same goes with the moment. We will take the summation of moment at point C. This force is causing a clockwise moment, so the resultant moment or the resisting moment of point C will be anti-clockwise, and it will be equal to the moment caused by this force of 540 Newton to maintain equilibrium. Example, you can see the figure numbers here because I have taken these examples from the R.C. Hibbeler book, and you can consult this book for further practice and for further reference material. Okay, in this example we need to determine the internal resultant loadings at the point C of the machine shaft. This shaft is supported by journal bearings at location A and B, which only exert vertical forces on the shaft. So we know that this point A and B is not offering any resistive forces to horizontal force or bending moments. We can determine the section forces on C by only determining the support reaction at A. Thus, first of all, we have determined what will be the resultant force of this distributed loading by multiplying the load with the length of that strip of loading along which it has been applied. Then we have taken a summation of moment at point B. We know that this point B or the support B is not resisting any moment, so the summation of moment at point B will be 0. Using this principle, this AY into this particular length plus the 120 Newton in this multiplied by 0.125 meter and minus 225 Newton into 0.1 meter, because this force will cause a clockwise movement, this force will cause an anti-clockwise movement, and as per our convention, we are assuming that AY will also cause a clockwise movement. However, the answer shows that our assumption was wrong. AY is actually acting in the downward direction. Thus, in reality, an anti-clockwise movement will occur due to AY at point B. Free body diagram of point C, as I've already mentioned that we are having a reaction force of 18.75 Newton at point A. This 40 Newton because we are considering point C and we cannot take the forces that are occurring beyond this point to determine the internal forces occurring at the point C. We were not having any horizontal forces, thus the summation of horizontal forces will be 0, and the internal force at point C, internal horizontal force at point C will also be 0. But internal vertical force at point C will be the sum of these forces acting behind this point, and this comes out to be minus 58.8 Newton. This means that internal loading at point C is also in the downward direction. Same goes with the summation of moments at point C. We have considered anti-clockwise moments as positive, but we are obtaining a negative answer, means that a clockwise moment of this value will act at point C to ensure equilibrium of that segment AC. Now we will discuss the summary of our lecture. First of all, we have discussed what is mechanics of materials, and the main thing in this discussion was that we will consider deformable bodies. And in deformable bodies, we do not only apply summation of forces to the external loads, we also need to consider the segments of a body to ensure that all the segments are in equilibrium with the external forces. Then external forces have basically two types. These are the surface or the body forces. Linearly distributed loading is a very important type of surface force because most of the loading on beams and these structures are the linearly distributed loadings. We need to ensure that we are considering the correct support reactions, and a support produces a force in a particular direction on its attached member if it prevents translation of the member in that direction, and it produces a couple moment on the member if it prevents rotation. The equations of equilibrium must be satisfied in order to prevent a body from translating with accelerated motion and from rotating. When applying the equations of equilibrium, it is important to first draw the free body diagram for the body in order to account for all the terms in the equations. Finally, the method of sections is used to determine the internal resultant loadings acting on the surface of the section body. In general, these resultants consist of a normal force, shear force, torsional moment, and bending moment. My advice or a homework for you people will be to practice examples in the mentioned books as well as practice exercise questions, because the more you will practice, the more stable your concepts will become, and it will become easier for you to apply these, because it is well said that don't practice until you get it right, practice until you can't get it wrong. Because when you sweat more in practice, you bleed less in war. Thanks for listening. You can ask your questions in the comments.